So let me just make it full. So all of you are able to see the slides? Hello? So all of you are able to see the slides? Hello?
Yes, ma'am.
Okay, so fair enough. So we started. So in the last class we stopped at the execution of the compiler, correct? Just a minute. Where is the retreat? Okay. So we're discussing about how the compiler compiles the program and executable is created. So we will now continue with that again. So we'll just review a little bit of the process of the compilation. So when you're translating a program from high-level language to low-level language, three system programs are involved. A system program is a program which will require some interaction with hardware. So some part of this software would be hardware dependent. So compiler, linker, and loader are three system programs. So compiler will be compiling a high-level language program into its machine equivalent. And while doing that, it will also create tables of incomplete instructions because some of the addresses is not resolved by compiler. Compiler cannot resolve these addresses, especially those belonging to library functions, because compiler has only access to the source code of the file. It doesn't know where the library functions are residing. And external variables, because at present the compiler will be looking at one file and then it will go to the next file, so it may not be able to resolve external variables. But it knows that these exist because you have included header files in case of C. So header files have got description of, have prototype or declaration of library function. So compiler will not generate any error knowing that linker is going to resolve that. Now linker will be resolving these addresses. So basically what linker will do, in case of static linking, the program code will be concatenated with library functions, library code, and the appropriate call instruction in the program code will be replaced by call to a certain address, and where address belongs to an address in the library file. But the problem in this approach is that your size of executable will increase. So if you have got, let's say, two programs, A and B, and both of them require access to standard library, so both the program would contain a copy of the standard library. So the memory requirement will increase. To overcome this, static linking is now being replaced by dynamic linking. So many of the libraries are dynamic linking library. So what happens in dynamic linking library, the operating system loads some of the most commonly used libraries and create a table where it keeps information about where each library file is located. And now the linker will only replace that this library file has to be called with this relative address. So only one copy of the library is maintained, and at runtime, the address will be resolved and the appropriate call will be made. So dynamic linking reduces the the memory overhead, but it may increase the execution time overhead a little bit. And then loader will load the copy of the program into the file. Now, when we look at a program, as I stated in the previous class, where each instruction is of the format opcode followed by requisite number of operands. Some of the operands may be implicit; they may be implied by the opcode itself. For example, pop. So everyone knows that something has to be taken out from the stack. But in some cases, you have to explicitly declare a operand. Similarly, in many of the instructions, accumulator, which is a special register, would be an implicit operand. So depending upon the instruction, the number of operands can be 0, 1, or 2. Anyhow, so ultimately the program will look like this. It will be a collection of this only. But if you look at the high-level language program, the high-level language program is consisting of different type of statements. These statements can be categorized into data declaration, where you are actually declaring that this is a symbol which I will be using in my program, and this symbol is of this type. For example, when you say int a, then a is a symbol that you are going to use in your program, and it will be of type integer. So you are telling the compiler that allocate 4 bytes for a memory space, which a memory location, which I'll be calling as a in my program. So here a is an identifier. So identifier is any name that is used in the program and that needs to be actually mapped to a memory location. So this could be a variable, this could be a constant, this could be a function name, or this could be label of an instruction. And another statement would be of type assignment. Then there could be expressions. There could be some control constructs like if, else, for, while, repeat until, etc. Do while, and there could be function calls. So now, as I said, that program is a collection of machine instruction, but if you look at high-level language program, it is having constructs other than the simple statements, or simple executable statements. So A equal to B is an assignment and it is an executable statement. So let's try to see how each statement would be converted into its machine equivalent. So when you're talking about a simple assignment, so basically the right-hand side operand has to be moved into memory, moved from memory to a register, and then this register has to be copied back to a different memory address which is belonging to X. So basically, here मैंने गलत लिख दिया है. Content of X should not be moved to accumulator. Content of Y has to be moved to accumulator. I'm sorry, this should be Y and this should be X. Okay, so this should be Y and this should be X. So content of Y is moved into accumulator and content of accumulator is moved into X. So Y and X will be actually appropriately replaced by their actual addresses, actual memory addresses. So right now, so this X and Y are the symbols, and assigning them a particular address, allocating memory to them is what the compiler will do. And once the compiler has done that, this particular statement will look something like this in the machine code. I'm showing here assembly code for clarity, and I'm not using any particular assembly language. This is just to make illustration. Now, if you have got an expression, expression needs to be broken into a sequence of sub-operation, where each sub-operation will contain only one operation and 2 operand depending upon what is supported by your machine. So if you look at this particular scenario, it requires 2 operations, addition and multiplication. And then depending upon the associativity and precedence of the operator, this expression, will be converted into sequence of 2 operations, B multiplied by C, and then A is added to it. So now all of you have done about infix to prefix and infix to postfix expression. So this is where the compiler will be utilizing those algorithms to determine in which order these expressions need to be evaluated. So So whenever such expressions will be encountered, they will be converted into a postfix expression, and accordingly the compiler will generate the code. Okay. So B is moved to the accumulator, then C is multiplied with it, and then A is added to it, and then you can store the result back to wherever it is desired. Now let's look at these constructs. There's nothing like if in assembly language or in machine language. So when we look at this particular statement, if statement, so what would be happening? First of all, the compiler will generate the code corresponding to condition. And then it will check whatever outcome comes, whatever result comes. Ultimately, condition will be nothing but an expression. And when an expression is evaluated, the ultimately result is in your accumulator. So depending upon the accumulator content, the action will be taken. So if the accumulator contents are 0, it means it is false. Otherwise, it is positive. So if it is not false, okay, here I have checked it against true again. So maybe we can check it against true. But if this condition is not true, then if this condition is equal to true, if this comparison matches, then accumulator contents will be 0. Otherwise, there will be no 0. So depending upon your machine, you have to check which flag will be raised when the condition is checked against true or false. But as I said, in most of the cases, condition would be actually evaluation of an expression, and that the final result will be in the accumulator. And depending upon the accumulator content, you can check whether that is true or false. And accordingly, this particular statement will change. Jump if not 0, jump on 0. So anyhow, if the condition is true, these two statements have to be executed, and then statement 3 has to be executed. But if this condition is false, then we have to directly go to statement 3. So this is what it is doing. So if the L2 statement. Here L2 is a label of an instruction. Please remember that you have not created this label in your source program, but ultimately while compiler is converting this into a machine equivalent program, then this label will come. So some of the labels will be generated by the compiler and not by you. So compiler has to know at which address statement 3 will be mapped. So compiler can do that only if it knows how much memory is required for condition, how much memory is required for statement 1, how much memory is required for statement 2, how much memory is required for checking condition, how much. So some of the instructions will be inserted by the compiler itself to ensure that this control flow construct performs properly. Any questions till now? Any questions? Okay. Then we come to while statement. So as long as this condition is true, statement 1 has to be executed. And the moment this condition becomes false, we should jump to statement 2. So again, so first of all, I'm sorry, again, this has to come down. Okay, just a minute. So this statement, this is where the statement will come. I'll make the correction. So first of all, the condition will be checked. And if it is true, then we'll come to statement 1. Otherwise, we'll jump to statement 2. There's a wrong, this one is incorrectly done. Yes, please.
मैम अगर हम यहाँ पे ट्रू के नीचे अगर स्टेटमेंट 1 डालते हैं तो फिर जो स्टेटमेंट 1 के ऑपरेशंस होंगे उनसे हमारे फ्लैग के वैल्यूज तो चेंज हो जाएंगे ना, तो अगर कंडीशन ट्रू भी हुआ तो अगले बार वो एग्जीक्यूट नहीं होगा.
Actually, that's what I was trying to tell you. This is not going to be like this. Maybe I can make correct this. Okay, I can correct it here only, and then I can bring it back. So basically, first of all, we are going to check statement condition and check condition equal to true or not. If condition is not true, then we go to statement this. Here we do statement 1 and then jump back without any condition to L1. This is how it will be. Okay. So I'm let me correct it now. Okay, this is how it will be. So it will check the condition. And if the condition, then it will check whether it will evaluate condition, write the code for evaluating condition, check condition whether it is true or not. If it is true, then flag will be set to, sorry, okay. If condition is true, then it is okay. Otherwise, if the condition is not true, it will the flag will be set to not 0, and then it will come to, if the comparison doesn't match, then the outcome of accumulator would be the difference of the two. So naturally it will not be equal to 0. So it will jump to statement 2 straight away. Otherwise it will come to statement 1 and then it will jump to L1 again. Once the statement 1 is executed, it will again check the condition. That's how it will work. Any questions now? Hello. Is that clear now? So first of all, you check the condition, then check what is the outcome of the condition, whether this outcome is equal to true or not. And if this is not true, then you jump to the statement 2 otherwise. So here at the machine level in instruction, you do not have any control construct. Basically, you are controlling the flow of the program through jump, conditional or unconditional jumps. That's all. Similarly, for the for statement, first of all, init will be evaluated. Then you check whether the condition is true or not, and then accordingly you do the statement. So if the condition is true, then you execute statement 1, apply, increment, and then jump back to checking the condition. If the condition is not true, then you jump to statement 2, which is coming outside the loop. So this is the assignment for you. So for example, if you have been given if else statement or switch statement, then how would you write the corresponding, how would the corresponding assembly language code or machine language code would be generated for these control blocks. And similarly for repeat until statement, and till now I did not show you, but what happens if I insert break and continue here? So what we are trying to say is that as far as the program code is concerned, once it is converted to assembly language, it is nothing but a collection of instruction where each instruction is of the type opcode and operand. And compiler is aware of that what is the size of each instruction by looking at the instruction itself, because the type of the operand is also fixed for each instruction at machine level. So once the compiler has generated the assembled code, it knows how much space each instruction is going to occupy. So it can calculate the space requirement for the program. The only problem would be the unresolved references, but each unresolved reference is an address and it knows how many bytes are required for each address. So the compiler is able to know the space requirement of the complete code. But what happens about dynamic scenario when a function is making call to another? So naturally, if a function is making call to another function, then and there might be recursion also. A function may call itself multiple times, and each call of the function to itself is another instance of the function. And for each instance, we have to reserve memory for its local variables. Am I right? So if function A is calling function B and function B calls itself again. So there are now two instances of function B, one which was called from A and one which was called from B. And it is quite possible that in both the cases, the local variables may have different values depending upon how the what were the input parameters. And for example, you all have gone through recursion, factorial n. So factorial 5 will make call to factorial 4, factorial 4 will make call to factorial 3. So in each of these, the input parameter value is changing. For first case, it is 5. For second case, it is 4, then 3, then 2, and so on. So naturally, we need to reserve spaces for different instances of the function. Can you tell me how it is done? Hello?
मैम स्टैक
Stack क्या करेगा?
मैम जितने बार फंक्शन कॉल होगा उतने बार स्टैक में फिर से ऐड होगा वो फंक्शन
फंक्शन ऐड
और
होगा?
फिर जब रिटर्न करेगा तब पॉप हो जाएगा।
फंक्शन ऐड हो जाएगा पूरा का पूरा?
नो मैम, फंक्शन कॉल ऐड होगा और फिर जब फंक्शन रिटर्न वैल्यू करेगा तो फिर वो पॉप हो जाएगा।
मैम प्रोग्राम काउंटर में अभी जो करंट नेक्स्ट इंस्ट्रक्शन की एड्रेस है वो स्टैक में स्टोर होगी, फिर वो नए एड्रेस पे जंप हो जाएगा और फिर
नहीं, फिर
रिटर्न
से
कर
बोलो,
सकते
फिर से बोलो।
सर मैम पहले तो जो हमारा इंस्ट्रक्शन प्रोग्राम चल रहा है तो प्रोग्राम काउंटर नेक्स्ट इंस्ट्रक्शन पे जो एग्जीक्यूट होने वाला था उस पे पॉइंट करेगा, उसको पहले स्टैक में स्टोर करा लेंगे और फिर उसके बाद क्योंकि कॉल फंक्शन आया तो वो उस एड्रेस पे जंप हो जाएगा और फिर पूरा एग्जीक्यूट होने के बाद रिटर्न जो होगा वो एड्रेस जो स्टैक के टॉप पे होगा वहां पर रिटर्न हो जाएगा।
स्टैक पे तो आपने कुछ डाला ही नहीं, अभी आपने मुझे बताया नहीं आपने स्टैक पे क्या डाला।
मैम प्रोग्राम काउंटर जो इनिशियली जो था कॉल से पहले
हाँ
नेक्स्ट इंस्ट्रक्शन का वो हमने स्टोर कराया था स्टैक के टॉप पे।
ठीक है।
हाँ मैम, फिर उसके बाद जंप करके सारे मतलब वो एग्जीक्यूट करके जब रिटर्न हुआ तो स्टैक के टॉप पे वापस एड्रेस रहेगा पहले वाले कॉलिंग फंक्शन का, वहां पर हम स्विच कर सकते हैं वापस।
और पैरामीटर्स और वो लोकल वेरिएबल्स का क्या होगा?
मैम लोकल वेरिएबल्स वो दूसरे सेक्शन में स्टोर होंगे ना मैम?
कौन से सेक्शन में?
मतलब स्टैक में स्टोर होंगे। एक सेकंड।
So let's come to the function call. So naturally, let's say function A makes call to function B, function B makes call to function C, function C makes call to function D. So A is making call to B, B is making call to C, C is making call to D. So which function will terminate first? A is making call to B, B is making call to C, C is making call to D. कौन सा फंक्शन सबसे पहले कंप्लीट होगा A, B, C, D में से? D. और D जब कंप्लीट होगा तो कंट्रोल कहाँ आ जाएगा? फ्लो कंट्रोल C के पास। फिर कौन सा फंक्शन कंप्लीट होगा?
C कंप्लीट होगा।
So as you can see that in this case, when a function call is made, the sequence of function completion of function is last in first out. So the last function called will be the first to be executed and completed. So this is similar to a stack. So here we can implement a stack structure to ensure that function calls are correctly executed and functions are executed in the correct context, where the context is the local variable and the environment space of that particular function. So what do we do when we call a function? What data we need to store and where do they go? And how do we return from a function? What data need to be restored and where do they come from? This is the question that we need to answer. So when we call a function, what data we need to store? We need to store what are the parameters to that function, and we need to store what are the local variables of that function. Am I right? But to ensure that we return back from that function to the correct, so calling function, so there are two things. One is the calling function and one is the called function. So function A is calling B. So calling function is A and called function is B. So when A is calling B, so we have to store the parameters of the B. We have to store the local variables of B. But when we return from B to A, we have to restore back the, as someone said, we have to come to the correct return address. So we have to store the return address also. So now we need to store parameters to the function, return address, and local variables. But naturally, when you're storing them onto the stack, and because number of parameters and number of local variables are not constant, not same across all the functions, so we do not know by how much our stack pointer has changed. So some of the stack pointer, so that we can return back to the correct value of address, correct value of the pointer. Correct value of the pointer. So we can now treat that for every function that is called, activation frame is pushed onto the stack. And when a program is, when a function is executing, it is able to access this activation frame. That's what we can visualize it as. So whenever a function is called, an activation frame is pushed, and what will be pushed onto this, what will this activation frame consist of? It will consist of parameters to the function, return address, local variables of the function, and old value of the stack pointer. So that when this function returns, the activation frame now on the stack belongs to the calling function. That's what we, so whenever a function is called, let's say something is pushed onto the stack, this something is called activation frame or activation record. And when we return back from the function, then we need to restore back to the activation frame of the previous function. Okay. So this is activation frame consisting of, I have written it here. So parameters to be passed. So first of all, you push the parameters to the function, then the return address, and then the old stack pointer value, and then the local variables of the called function. So what calling function will do? So now this is it. So calling function will, okay. So here P is making call to Q. So as you can see, we push the, so P is going to push the parameter to the function because P knows with which value parameter to the function will be calling. Push the value of old frame pointer so that when the call returns back from Q to P, the activation frame of P is now available on the stack. And then the local variables of Q are pushed, and this is now the stack pointer is occurring at this point. So now all the local variables are with respect to the stack pointer, and they can be accessed accordingly. So this will be the role of this. Calling function will push arguments onto the stack in the reverse order. Why reverse order? So that, so if the function is being called with the 3 parameters A, B, and C, so it will first of all push C and then B and then A, so that A is nearest to the stack pointer, new stack pointer. Then it will push the address of the instruction, and then it will make a call to the function, means the control will now go to the function itself. And now it will now save the previous value, push the set current frame pointer to where the end of the state pointer is now, and push the local variables onto the stack. So this is how it will be done. So this is how the activation record will look like. And now when the activation frame is removed, so basically we do not remove any data from the stack, we simply move the stack pointers to the correct value, so that now the activation record frame is pointing to the correct function. That's all. We do not remove anything from the stack. And because of that, there could be the stack is not cleaned after the control returns back to the calling function. So it means
Ma'am.
if we have, yes, please.
मैम एक्टिवेशन फ्रेम क्या होता है?
अब वही तो मैं समझा रही थी वो कि जब आप कोई फंक्शन कॉल करते हैं तो फंक्शन कॉल करने के लिए टू एंश्योर दैट द फंक्शन इज कॉल्ड प्रॉपरली एंड देन इट कंट्रोल एंड देन इट रिटर्न्स बैक टू द करेक्ट एड्रेस, compiler ensures that a compiler maintains a data structure which is activation frame, and this activation frame is pushed onto the stack with every function call. And this activation frame will consist of parameters to the function, return address जहाँ पे वापस रिटर्न करेगा वो फंक्शन कॉल हो जाएगा, उसके बाद लोकल वेरिएबल्स, एंड क्योंकि स्टैक वापस आपको पूरा ढंग से मेंटेन करना है तो स्टैक पॉइंटर्स रखेगा, ओल्ड स्टैक पॉइंटर रखेगा। तो अभी आप मान के चल लीजिए कि आपका ऑपरेटिंग सिस्टम ने फंक्शन को कॉल किया है, तो ऑपरेटिंग सिस्टम जब फंक्शन को कॉल करेगा वो आपका मेन फंक्शन होगा, एम आई राइट? और मेन फंक्शन में अगर आप कमांड लाइन आर्ग्यूमेंट इस्तेमाल कर रहे हैं तो वो कमांड लाइन आर्ग्यूमेंट आपके मेन फंक्शन को नहीं पता है, आपके प्रोग्राम को नहीं पता है, वो सिर्फ ऑपरेटिंग सिस्टम को पता है, क्योंकि आपने कमांड लाइन कहाँ टाइप की है? ऑपरेटिंग सिस्टम पे, है ना?
ऑपरेटिंग सिस्टम,
एम आई राइट? तो अब क्या होगा कि ठीक है, तो ऑपरेटिंग सिस्टम जहां पे स्टैक पॉइंटर है उस स्टैक पॉइंटर पे वो सबसे पहले पुश करेगा आपके आर्ग्यूमेंट्स कि ये आर्ग्यूमेंट जो कमांड लाइन आर्ग्यूमेंट है, राइट और नॉट राइट टिल दिस पॉइंट?
यस मैम।
पर जैसे वो पुश करेगा स्टैक पॉइंटर चेंज होता चला जाएगा, है ना? स्टैक पॉइंटर चेंज हो जाएगा ना, जब भी आप कोई चीज पुश करोगे तो स्टैक पॉइंटर चेंज होगा ना?
यस मैम।
ठीक है, तो अब मान लो मुझे वापस फंक्शन से रिटर्न करना है, तो मुझे वापस स्टैक पॉइंटर को रिस्टोर करना है, तो मैं कैसे रिस्टोर करूंगी? तो मुझे कहीं ना कहीं ओल्ड वैल्यू ऑफ स्टैक पॉइंटर भी पुश करनी पड़ेगी।
यस मैम।
ठीक है, तो जनरली दो पॉइंटर्स रखते हैं, बेस पॉइंटर और स्टैक पॉइंटर। तो बेस पॉइंटर में अभी मान के चलो कि जब आप एक्टिवेशन रिकॉर्ड डाल रहे हो तो एक बेस पॉइंटर और एक स्टैक पॉइंटर है, ठीक है, बेस पॉइंट, ठीक है, और बेस पॉइंटर इज राइट नाउ इक्वल टू द टॉप ऑफ द स्टैक। अब आप स्टैक पॉइंटर पे अब आप जब कमांड लाइन आर्ग्यूमेंट डालोगे तो स्टैक पॉइंटर मूव होना शुरू हो जाएगा, और उसके बाद में फंक्शन कॉल जब आप मेन से रिटर्न करोगे तो ऑपरेटिंग सिस्टम में कहां रिटर्न करोगे वापस? तो उसका एड्रेस आएगा, दैट इज द रिटर्न एड्रेस। ठीक है,
तो मैम मेन फंक्शन का भी एक्टिवेशन फ्रेम होगा क्या?
ये मेन फंक्शन का ही एक्टिवेशन फ्रेम बता रही हूं मैं।
अच्छा, यस मैम।
किसी भी फंक्शन का एक्टिवेशन फ्रेम में पहले उसके पैरामीटर, रिटर्न एड्रेस, फिर ओल्ड वैल्यू ऑफ द स्टैक पॉइंटर एंड देन लोकल वेरिएबल्स आएंगे। पर ये जो पुश करने का पार्ट है, दिस विल बी डिवाइडेड अक्रॉस टू थिंग्स, वन इज द कॉलिंग फंक्शन एंड वन इज द कॉल्ड फंक्शन। दैट्स व्हाट आई वाज ट्राइंग टू एक्सप्लेन। क्योंकि जो कॉल्ड फंक्शन है उसको नहीं पता है कि पैरामीटर की वैल्यू क्या है। पैरामीटर की वैल्यू किसको पता है? कॉलिंग फंक्शन।
कॉलिंग फंक्शन।
तो कॉलिंग फंक्शन पैरामीटर्स पुश करेगा इन रिवर्स ऑर्डर। उसी को पता है कि कंट्रोल वापस कहाँ आना है, क्योंकि उसको पता है कि अभी प्रोग्राम काउंटर की वैल्यू क्या है, तो वो प्रोग्राम काउंटर की वैल्यू वहां डालेगा जहां पे रिटर्न एड्रेस आना चाहिए, वापस वो नेक्स्ट इंस्ट्रक्शन पे आना चाहिए, तो प्रोग्राम काउंटर +1 या जो भी वो वहां पे डालेगा। उसके बाद में उसको मालूम है कि अभी बेस पॉइंटर की वैल्यू क्या है, वो बेस पॉइंटर की वैल्यू पुश करेगा। ठीक है, अब कंट्रोल आ जाएगा कॉल फंक्शन के पास, उसके बाद कॉल फंक्शन को कॉल कर देगा। कॉल फंक्शन अब अपने लोकल वेरिएबल्स पुश करेगा, और अब स्टैक पॉइंटर जहां पे है सारे लोकल वेरिएबल्स जो ट्रांसलेटेड होंगे वो स्टैक पॉइंटर के रिस्पेक्ट में होंगे कि स्टैक पॉइंटर से कितनी ऑफसेट पे है ये लोकल वेरिएबल्स। So now because this particular thing is being done by compiler, because this code is not written by you anywhere in your program, so the compiler only does this at the, so ये जो मशीन लेवल में सब so जो भी पुश करना है स्टैक पे, ये जो कोड है that will be inserted by compiler. And now compiler knows कि how many arguments have been pushed, how many parameters have been pushed. Compiler knows what is the space of the local variable. So compiler knows कि stack pointer से कितनी दूरी पे क्या चीज अवेलेबल है। Are you with me now?
Yes, ma'am. Thank you.
And ठीक है, so this is not visible to us, but this is being done at the compiler level. So what exactly I'm trying to tell you is that there are two things in your program. One is your simple instructions, which will be converted into machine level instructions, high level instructions, which may be converted into a sequence of machine level instructions. And then there are control flow constructs. And these control flow constructs are if, else, for, while, etc., and call to the function. But these are also resolved into machine level instructions. But for calling function, we need another thing that is called stack. It means program को सिर्फ machine level equivalent में convert करने से काम नहीं चलेगा, हमको उसको extra memory भी देनी पड़ेगी और उस extra memory को as a stack इस्तेमाल किया जाएगा. Are you with me now?
Yes,
So
ma'am.
high level language program, and it is converted to a machine level program, then it will consist of the instructions plus some memory that has to be used as a stack. And what this stack will be used? This stack will be used for maintaining. This stack will be used for implementing function calls. So whenever you're making a call to a function, you need to preserve its local variables. तो जैसे अगर मान लीजिए एक ही फंक्शन को दो डिफरेंट कॉल आपने कर दिया, फंक्शन ए ने फंक्शन बी को कॉल किया, फंक्शन बी ने वापस फंक्शन बी को कॉल किया, so there may be recursive calls also. So at each instance of this function b, the local variable space may change. Local variables may have different values, parameters may have different values. So you cannot use a single activation record for b. For different call to b, different activation record should be used. And that can be done only if you use stack. Is it clear now?
Yes, ma'am. Thank you.
Then there is another thing. In most of programs, we also make use of pointers. And we are allocating memory at runtime by using malloc, calloc, library calls. So now naturally, this memory is not, the compiler does not know how much memory will be required, because this malloc will be executed at runtime and parameters are being caused to being passed on to malloc. So compiler may not be aware of this size. So because they may be dependent upon user parameter, you may ask what should be the size of array. The user says 10. The compiler doesn't know what value user will supply. So compiler cannot know how much memory will be allocated at runtime. So for these runtimes, another memory area is reserved for the program, and this is known as heap. Are you with me now? So now it means when we are looking at a process, when this program will be loaded into the memory, it is not just collection of machine language instructions. It also should have some memory for stack and some memory for heap. So ultimately, the abstraction of the program from the operating system perspective would be collection of these three things. Okay, so I'll come to this first of all. So as far as a user is concerned, the program file consists of a global data and program machine code. But ultimately, when it is loaded into the memory, you also need to keep some space for stack and heap. Okay, and this stack and heap, generally the way they are organized, they grow in opposite direction. This is for the efficient utilization of the space, because you can reserve only a fixed amount of space for both of them. So if the stack grows more and heap is still empty, you can allow the stack to grow. If you allow stack to grow from, let's say, top to bottom and heap from bottom to top. So if they grow in opposite direction, then the space can be efficiently utilized. Okay. Now, apart from that, operating system also needs to keep data structure to ensure that this process can be executed correctly. And this will be process control block, and there will be some other kernel data structures which will be used to ensure that this process can run properly. We'll come to it later. We'll come to it in slide. Bear with me a little bit. So we said when the compiler compiles the code will be just collection of machine level instructions, and the control constructs actually gets transformed to conditional and unconditional jump at machine level. Secondly, when we are trying to implement function calls, we need extra space, and this space has to be utilized in the form of stack. And basically, we are pushing an activation frame or activation record per function call. But when what we are pushing onto this activation frame or activation record, the division of this work is divided across calling function and called function, because calling function is not aware of the local variable space and called function is not aware of the argument that are being passed to it. So the pushing of argument is left to calling function and pushing of local variable is left to call function. So basically this machine instruction code which does this activity is inserted by compiler for every function call. So now it means we need extra space for managing stack, and we also need extra space for managing heap. So ultimately, as far as compiler is concerned, it has to allocate memory not only for the program, it also has to have additional memory for heap and stack. And when we are loading the program, we are actually ensuring that this entire space, so if the program का size अगर 100 किलोबाइट था और हमारा heap 40 किलोबाइट है और हमारा stack 40 किलोबाइट है, तो हमें 180 किलोबाइट की memory चाहिए main memory में, so that we can execute this program. That's what it actually means. Is that clear to everyone now? Is that clear to everyone? Any questions? Any questions? Okay, so we'll continue further. If there are any questions, you can post it on WhatsApp group. Okay. So the problem is that an absolute loader will take the program and copy it into a certain part of the memory. But what if we need to change this location? So let's say because once the compiler has generated the addresses, these addresses will remain same, isn't it? So if it says that 5,200 and symbol B has been assigned address 5,300, so they were with respect to 5,000. But now if the program is shifted to 7,000, the whole scenario will change. So these address needs to be translated accordingly. But do we need to translate each and every address? No. Some of the addresses are relative address. Jump plus 23, jump minus 28. So these relative addresses need not be changed. So now a relocatable loader has to ensure that all absolute addresses are translated accordingly, but all relative addresses are left as such. So as we said, that a process is a program in execution, and process, as I told earlier right now also, it will consist of the program code. But apart from that, it will require some memory for stack, some memory for heap. And of course, there will be some data section containing global variables and some text section containing program code. Apart from that, it may also need to keep some information about its current activity. So this is how the address space of a process will look like. So this is the text section. This may be global data, which is initialized or non-initialized. Why I'm talking about uninitialized data, for example, if you're keeping a global pointer, the pointer may not be allocated the memory. Then this is the heap from which the runtime memory will be allocated, and the stack, which will be used for maintaining activation record when the functions are called. And then when the process starts, something will be pushed onto the stack, and that will be your command line and environment argument, which will be pushed by operating system. So as I said, this is a program. Program is just a collection of global data and program machine code. But when this is loaded into the memory, this is process, and in this process, stack, heap, process control block, and there'll be some kernel data structure. Basically, operating system will maintain a data structure called process table, in which it will keep information about each process. What information it will keep? What is the ID of the process? You name a process by a name, but operating system will assign it an integer ID. So what is the process ID? What is the name of the process? Who is the owner of the process, etc., etc. It will keep some information about that. And then a pointer to the process control block. So what is shown here as gray is actually being managed by operating system on behalf of the program. So that's why we have shown it in gray. And before that, let's come to the process control block, also known as process descriptor, and we keep one process control block per process. So information that it keeps will be the ID of the process, who is the owner of the process, what are the privileges, what is the state of the process, what are the children of the process, and what are the other processes which are interacting with it. And if there are some inter-process communication, then it will keep information about whether the signal has been sent, whether the signal is awaited, what are the flags, what are the messages that are being pending to be sent or pending to be processed, etc. Then the state of the program, context of the program, that will be program counter and the CPU registers. Because a process will be scheduled, so it may be a priority scheduling, so it will try to keep information about that and so on. Now, state of a process. When a process is created, so a user says, I want to run a program. So naturally, a new process is created. What we mean by new process? The program is loaded into the memory, and operating system will assign will allocate a program control block for this process. Operating system will create an entry for this process in the process table, and the process will be added to the queue of processes waiting for CPU to become available. So this process will now join ready to run process. Ready to run processes are the processes which are not waiting for any event, and they are ready to be executed on the CPU. So when the process gets is scheduled, is allocated memory, when the process is scheduled, it is allocated CPU certain time, which we call quantum, the process is returned back to the queue of running processes because another process has to be given chance. However, before the quantum is over, if the process gets finished, it will go to terminated stage. At this point, all the data structure where this process was entered by the operating system, these data structure will be cleaned of this process. If the process is running, but it requires an input-output event, its quantum is not over, it requires an input-output event, it goes into blocked or waiting stage. So basically, it is put into a queue for input-output processor. So now so once it gets scheduled onto the input-output processor and input-output event gets completed, it returns back to ready process. Now, sometimes if the new processes are coming at a higher rate, some of the old processes which are in the memory or which are waiting for an input-output event may be swapped to hard disk. So a hard disk contains what we call a swapped area where these processes can be shifted by operating system. So if a ready process is swapped out, and after some time, if there are less processes in the memory, it can be swapped in. So when a ready process is swapped out, so after swapping, it will again join the ready to run queue. But if a block process is swapped out, it will again join the queue of block process. So it is not that when the block process is swapped out, it can be swapped in back to ready process. It cannot be because it is still waiting for an event to happen. So this is the process state diagram. Okay. And there is something called context of a process. So if a program was executing, and let's say it was executing instruction at address X, if the context, if this process is deallocated CPU, the CPU is taken away from this process and given to another process. So when this process starts, it should start from the same address. Okay, but not only it should start from the same address, the content of all the registers should be the same as when it was taken away from the CPU, when the CPU was taken away from this process. So the content of all the registers of a process is known as context. Apart from that, the last instruction might have allocated a resource to this process. So naturally, the list of the resources allocated to this process may also have changed. So context of a process will be the CPU registers, which will also involve program counter, but it will also consist of all the resources allocated to this process, which is like file descriptor opened by the process. It may be related to accounting information, because when the process is switched, then some accounting information may have to be updated so as to ensure that the process may be charged according to the CPU that has been used or memory that has been utilized. So context of a process will consist of these things. So naturally, when a process A is running, and if the CPU is given to process B, before the CPU can be given to process B, context of process A should be saved. And B should be resumed from the saved context of B. So if B was running before, and now if B is resumed back, so its saved context has to be restored. So all the values of the registers which were saved, they have to be loaded into the CPU. So this is what it means. So in the next class, we'll be talking about context switching of a process, and these are some assignments that you have to do. So I explained the first assignment. Okay, now the second assignment is you have to study GCC command. GCC command is for invoking C compiler on Linux, that is GNU C compiler. And then you have to see how you can use this GCC compiler to link to. In fact, most of the compilers are actually compile and link. They use linker also. So they invoke linker also. So how can you link to different libraries? What are the optimization related options? How can you generate only the assembly output? And if you find any other option which is of interest, please write it down. Then there is another command called PS, that is process status. So you have to know what is it, and then you have to give me some information about it, and what useful information do you think you can gain from this. So I will expect you to execute these commands and try to tell me the information. So these two assignments will become part of the coursework, and I'll be setting the deadline in the classroom for you to submit it. Most probably you have to submit it by tomorrow. So anyhow, have a good day. If there are any questions, it's okay. Otherwise, thank you all for being here. Any questions? Any questions?
मैम
Okay, so I'll just take the attendance. Yeah, please.
मैम जब दूसरे किसी रेडी स्टेट वाले प्रोसेस को हम स्विच करते हैं, कॉन्टेक्स्ट स्विचिंग करते हैं, तो फिर जो हमारा पहले से रनिंग है उसका जो हम कॉन्टेक्स्ट स्टोर करते हैं, तो फिर वो वहीं पे रहने देते हैं या फिर कहीं और पे कॉपी करते हैं?
एक्चुअली कहीं और पे कॉपी करेंगे, उसके स्टैक पे कॉपी करेंगे.
ओके मैम,
ठीक है ना? ठीक है, तो मैंने एक क्वेश्चन पूछा है, आप उसको आंसर कर दीजिए. For the attendance sake, just answer that question. So I'm closing the meet, and you can actually continue with your answer on the classroom.